As successful as the Big Bang Theory is in explaining the early evolution of the universe, it left some unsolved problems. Why is the universe so isotropic and homogeneous? An explosion in empty space will not result in an isotropic homogeneous universe. Why is there structure and how does that come about? Why does the geometry of the universe around us look so flat? Unification theories of physics tell us that particles called magnetic monopoles should have been created in copious amounts during the Big Bang. Where are they? These were some questions that needed addressing. Physicists Alan Guth and Andre Linde independently worked out a scenario called inflation that could explain these remaining questions. It is commonly believed that space and time emerged from the Big Bang, like all the matter, radiation and energy. Inflation is a rapid expansion of space that occurred sometime before 10 to the minus 32 seconds after the beginning of the universe. That is, before the universe was a 100 million trillion trillionth of a second old. The universe expanded by a factor of 10 to the 60th power in less than 10 to the minus 33 seconds. That is, it grew by a factor of a trillion times in less than 1 billion trillion trillionth of a second. It gave the universe such a tremendous push that it has been expanding ever since. In looking at this illustration representing the expanding universe, one has to realize that there would be no way to view it from somewhere outside. There simply is no outside. Space itself is created in the Big Bang and the expansion is creating more space. According to modern versions of inflation, the universe started out with what physicists call the inflaton field in a very high potential energy state. This was a very unstable situation. There was very little initial expansion at this point. An event triggered a phase change and the inflaton field started rapidly expanding space while slowly losing energy. This is sometimes called slow roll inflation. The field then decays and the energy heats or reheats the universe. This rapid expansion and heating puts the bang in the Big Bang Theory. The present value of this field may not be zero and may have some connection with dark energy, which is discussed in Chapter 22. The energy dumped into the universe starts the particle-antiparticle pair creation and annihilation that is part of the original Big Bang Theory. The universe may have started with a high temperature, then the expansion cooled it. After the decay of the inflaton field, the universe is reheated, but probably not to as high of temperature. One of the problems addressed by inflation is the question of how structure arises. Why is the universe not simply a perfectly homogeneous distribution of hydrogen and helium? How is the universe today full of structures such as galaxies, stars and planets? Quantum physics tells us that any energy field will necessarily undergo fluctuations at the microscopic scales. These quantum fluctuations were occurring when the universe came about. Inflation not only expanded space, but it also inflated those energy fluctuations. There were regions in the universe that had a bit more energy than other places. In those places more matter would be created, making those places denser. Locations with greater density had more gravity and would gravitationally draw in even more matter from less dense regions. Where matter was drawn together, clusters and superclusters of galaxies would later form. Why is the early universe so uniform in temperature? The cosmic microwave background shows that it was incredibly uniform only 380,000 years after the Big Bang. In everyday systems at different temperatures, they can come to the same temperature, achieving thermal equilibrium by the transfer of energy. However, the maximum speed that energy can be transferred is the speed of light. Regions greater than about 2 degrees separation in the CMB map would not have had time, since the universe began, to have established thermal equilibrium. Inflation tells us that when the universe formed, there wasn't an instantaneous expansion. The universe may have come to thermal equilibrium when it was incredibly small. When it inflated, it maintained that pre-established equilibrium. Recall that the universe has a global geometry. It is either open, closed or flat. Why does the universe look so flat? Flatness would take an amazing amount of fine-tuning as far as the expansion rate and the mass energy content. If we remember that inflation is literally an inflation of space, then regardless of the overall geometry, the universe will appear flat. It is like the expansion of a balloon with an ant riding along with the expansion. To the ant, the surface of the balloon looks flatter and flatter as the balloon expands. In the expanding universe, any non-uniformities in the geometry would be flattened out and the global geometry would appear flat. This helps to explain the homogeneity and isotropy observed in the universe today. Measurements of the CMB has shown us that the universe indeed seems to be amazingly flat. Lastly, there is what is often referred to as the magnetic monopole problem. All observations and experiments that have ever been performed thus far show us that magnetic north poles are always accompanied by magnetic south poles. Breaking a bar magnet still gives you two small bar magnets, each with a magnetic north and south pole. Magnetic monopoles, particles predicted to exist by almost all unification theories, are particles with magnetic north without a magnetic south or south without the north. None have ever been observed in nature. The argument is that these particles would be very massive and creating them would require energies not yet achievable in modern particle accelerator laboratories. However, in the high temperature of the early universe, there should have been copious numbers of them created. Why don't we ever find any? When the universe first came into existence, the temperature may have indeed been high enough to create magnetic monopoles. Inflation cooled the universe and quickly ended monopole creation. After inflation, the reheating may not have increased the temperature of the universe high enough to form more monopoles. The few that were initially created were scattered all over the universe during inflation. They may be out there, but finding any would be extremely unlikely.